In today's video, we're going to explore how we can use experimental data to determine a rate law for a reaction. Usually, reaction rates have to be determined experimentally. A common experimental approach to the determination of rate laws is called the method of initial rates. This method involves measuring reaction rates from multiple experimental trials that are carried out using different initial reactant concentrations. Comparing the measured rates for these trials can help you determine the reaction orders and the rate constant. From this information, you can formulate a rate law. Here's how it works. First, you measure the instantaneous reaction rate immediately after you mix the reactants. And then you repeat this over several trials, but for each trial, you vary the concentration of one of the reactants. You compare these runs to help figure out how the concentration of each reactant affects the initial rate. Look at the data. Does the rate double? Does it quadruple? Does it stay the same? This will help you figure out what the rate law is. Here's an example. Let's say we have the chemical reaction, 2 moles of nitrogen monoxide reacts with 1 mole of chlorine gas to form 2 moles of NaCl, or nitrosyl chloride. The following initial rates were determined experimentally. Now, we know our rate law is going to have the form rate equals K, with the concentration of nitrogen monoxide taken to the M power and the concentration of the chlorine taken to the N power. There are 2 ways we can do this. The first one is to compare the ratio of rates to the ratio of concentrations during 2 different time periods. So let's first look at trials 1 and 2, where the concentration of chlorine is held constant. We're going to take our rate law for the first trial, that little subscript 1 says this is trial 1, and we're going to divide that rate law by the rate law for the second trial with our subscript 2. And now we can look at the table and put in the numbers that correspond to these values. And since the concentration of the chlorine doesn't change, we can just cross that out. And if we simplify, we have 1/4 equals 1/2 to the M power. Now let's think backwards. What power would we have to take 1/2 to get 1/4? Well, if we were to square 1/2, we would get 1/4. Hence, M has to equal 2. We'll do the same thing with trials 2 and 3, where nitrogen monoxide is held constant. We're going to divide the whole rate law for trial 2 over the rate law for trial 3. And we put in our numbers, and since the concentration of nitrogen monoxide doesn't change, those are going to cancel out. Simplify it, and we see that 1/2 equals 1/2 to the M power. So if we take 1/2 to the first power, we get 1/2, so N would have to equal 1. We can rewrite our rate law as this. Rate equals K times the concentration of nitrogen monoxide taken to the second power times the concentration of chlorine. We can also determine the rate law by inspecting the table. If we compare trials 1 and 2, if we double the concentration of nitrogen monoxide while holding chlorine constant, the rate quadruples, and this suggests a second-order reaction. If we compare trials 2 and 3, where chlorine is doubled and nitrogen monoxide is held constant, we see that the rate doubles, and this suggests a first-order reaction, hence N equals 1. We can rewrite our rate law as rate equals K times the concentration of nitrogen monoxide squared times the concentration of chlorine, and that's to the first power, and we don't need to put a 1 on that because it's assumed. Here's another example. Ozone in the upper atmosphere is depleted when it reacts with nitrogen oxides. The rates of the reactions of the nitrogen oxides with ozone are important factors in deciding how significant these reactions are in the formation of the ozone hole over Antarctica. One such reaction is the combination of nitric oxide, NO, with ozone, O3. And note that nitric oxide is another name for nitrogen monoxide. Here's the chemical equation. We're told that the reaction has been studied in the laboratory and the following rate data were determined at 25 degrees Celsius. We're asked to determine the rate law and the rate constant for the reaction at this temperature. Now we know the rate law is going to have the form rate equals K times the concentration of NO to the nth power times the concentration of ozone to the nth power. And we should be able to use experimental data to determine M, N, and K. We could do this by looking at ratios of rates and concentrations like we did in the previous example, or we could do it by inspection. Let's do it by inspection. First, we're going to find the M, the order that's on the nitrogen monoxide. Notice that when the concentration of NO doubles, the rate also doubles. When the concentration of NO triples, the rate also triples. So the order of this reaction in NO is 1. We're going to now find N, the order of the reaction in ozone. Notice that when the concentration of ozone doubles in trials 1 and 2, the rate also doubles. When the concentration of ozone triples in trials 1 and 3, the rate also triples. So the order of the reaction in O3, in ozone, is 1. And our rate law is rate equals K times the concentration of nitrogen monoxide times the concentration of ozone, and both of those are to the first power. To find our rate constant, we're going to write our rate equation, and then we're going to rearrange it algebraically and substitute in values. We're going to take some values from the table, and we could take them from any of the trials, and we're just going to substitute them in here. Make sure you include your units. This will help make sure you get the right units for K. And once we do, we get 2.20 times 10 to the negative 7th moles per liter per second. In summary, experimental methods can be used to monitor the amounts of reactants and/or products of a reaction and to determine the rate of the reaction. Comparing initial rates of a reaction is a method to determine the order with respect to each reactant.